Welcome to my YouTube channel, Lead Art Sci. Lead is for literature, art is for art, and sci is for science. My name is Zeinab Kordi. I have PhD in physics. In today's video, I would like to talk about Casimir effect. I was searching about this topic when I was PhD fellow at Center for Theoretical Physics, Polish Academy of Science, CFT in Warsaw. And also the idea actually was given by one of my physics teacher at the University of Shenzhen when I was master student. Okay, let's move on. Why Casimir effect is important and what is the history behind of this effect. So at the beginning, I will talk about a little bit history of Casimir effect. And then I will talk about quantum field theory. So what is quantum? In previous videos, I was talking about quantum world, very, very small scale universe. Field theory, so it's, I will talk about it in details and with some animations. What do I mean of field theory? And so quantum field theory. So the field should be quantized. The field should be treated as a quantum object. Okay, so then I will talk about vacuum fluctuation. Do you think that vacuum is really empty of everything, or there is something even in vacuum? So we will answer this question. I will talk about it. And the Casimir effect and MEMS. MEMS is the abbreviation of micro mechanical machines. It's very, very small scale machines that are actually the Casimir effect and Casimir force can be used in this very, very small scales machine. Okay, and then conclusion, some references that I was using in that time. And okay, so Casimir force. First time the Casimir effect was discovered by a Dutch physicist, Hendrik Casimir. So what is Casimir effect? As you know, in electricity, in magnetism, so we define a force between two charges. So the electrons, protons can create electric field on each other. So that is called electric field. But in Casimir effect, also there is, so Casimir discovered that, let me listen back again to the previous, so you see, this is two conductor plates that they are placed in a very, very small distance of each other. So this conductor plates, actually, there is no charge on this plates, but they are conductor. And when there is a very, very small distance between these two conductors, so this distance should be in order of nanometer. So 10 nanometer, 9 nanometer, 1 nanometer. And in this small scale of distance between these two conductors, Casimir discovered special effect, special force. And this force that there is between these two plates, he just called it Casimir effect. So this is the picture of Casimir and his colleagues in that time. But when we say that they actually create a force on each other, these two conductor plates, how we can define this force? So vacuum is not empty, even vacuum. So we have actually, but in these two plates, the type of the force is quantum force, and there is quantum fluctuations between these two plates. And when we are talking about quantum fluctuation and quantum force, we have to use, for example, for each pack, h bar nu. H is the Planck constant that it was measured by Planck. And so we have to use a lot of, we have to treat the particles as like photons with a pack of the energy. And then this force actually is applied on a special area of each plate. This area can be defined by S, and C is the speed of the light, and P is the P constant, and D is the distance between these two plates. So Casimir, for the first time in 1948, could measure the force between two conducting parallel plates of area S spaced by D. So we know that in every measurement there is uncertainty. That was the first measurement by Casimir, and you see the order of magnitude is very, very small, 10 to minus 27 Newton. Okay, so FC, Casimir force. So let's move on and let's see what is fluctuation, what is quantum fluctuations, and a little bit from the theory that it was predicted by Casimir, and the other experiment that came after this prediction. Okay, so first attempt, I was talking about it, was done by Casimir, and also in 1958, Sparnai, MJ Sparnai, did the first attempt to measure the Casimir force in laboratory. Second attempt and first successful result was done in 1996 by Stephen Lamoureux in agreement with theory to, so the uncertainty was 5%. And the other measurement was done by Mohyeddin and Anushri Roy in 1998. And several other successful experiments also have been done. So they could detect the Casimir force in laboratory by using, for example, the atomic force microscope. They could measure the Casimir force in laboratory and experimentally. Okay. In this picture, you could see the AFM cantilever. You could see here. So to explain what's happening in AFM microscope, this is a microscope that is working with atomic force. So it means that you have to focus on the forces that is happening between the atoms by applying the laser. So you apply the laser on the surface on a special plate that you want to study, and there is a sphere here, there is a tip. This tip usually is used by AU because it should be so reflective. And there is a cantilever here, and when this laser is applying to this cantilever and this tip could actually detect how much this laser create a change in this plate. So, and then there is a photo diode here, and in this photodiode, this photon actually can be the photon which is reflected already from the surface and the plate can be detected in this photodiode here. So this is the schematic diagram of the experimental setup. Application of voltage to the piezo result in the movement of the plate towards the sphere. The experiments were done at the pressure of 50 millitorr and at room temperature. So basically, when this laser creates a little small force on this atom on the surface of the plate, so this force is very, very small, but can create actually a change on the surface of this plate. So scanning electron microscope image of the metallized sphere mounted on a AFM cantilever. The people who are expert in this experiment and who are working with this, so they definitely have more details to say. I just put this picture to show how you could detect such small forces, for example, in AFM microscope. So, and by using the AFM microscope, they could measure the Casimir force, and the plate sphere separation was the order of nanometer. And so the Casimir force, as I showed you, it's the order of 10 to minus 20 something nanometer. Okay, so this was done experimentally. And you see that, as I told you, the sphere is coated by AU. It's the optical fiber. The distance from the tip and to the surface is measured, and so we can actually use a micro machine oscillator to measure this force for Casimir force. Okay. And as you can see here, for example, if we consider our target atom here, after applying the laser and after applying the force, so you see that a little bit change on the surface, and this movement of this targeted atom from here to here, from this distance to this distance, actually is done by the force field, by the force that is carried by light to this surface. Okay. This is AFM image of the AU plane before and after force measurement. I already explained it to you. And so I told you that that the type of this field is quantum, is not classical. So what does it mean? It means that it is quantized. It's not continuous. It is a pack of the energy, and we have to define something like virtual particle to explain the physics behind of this two parallel conductor plates which could create force on each other. Okay, so here you can see an electron, a positron, and this is space, and in a space, in every second and every time, there is always spontaneous emission. There is always the interaction between particles and antiparticles. So interaction here, for example, between electron and positron. So when they interact with each other in fundamental particle, we know that they could create a ray, a gamma ray, so X-ray. So here they could create the gamma ray, and so it means that a particle can be, this is about E equal mc squared. So it's about the conversion of mass and energy in the space. And when the particle is small enough, it means that the mass is very, very, very small, and the speed of the particle is very, very is very big and high, close to the speed of light. Then we have something relativistic. It is happening in space that even Dirac was thinking about it, and so on. So we have quantum field theory, and also Feynman was describing this kind of interaction between the particles and the photons. So gamma ray is photon. So this is the conversion of the electron and photon. So positron, you could see here, for example, I didn't study nuclear physics, so this is just a picture. And for example, the people who studied this, they know that unstable radio nuclei, they could create rays. So this ray can be even harmful for health sometimes. Okay, so but vacuum fluctuation. So if we have a vacuum. So what does vacuum mean? Always we say that vacuum is a special environment that there is nothing in it. But vacuum is not really vacuum. So in quantum scale, there are something that we call it quantum fluctuation. And the quantum field theory can appear in vacuum even. Okay. So the vacuum cannot have absolute zero energy. That would violate Heisenberg uncertainty principle. So we know about Heisenberg uncertainty principle. It means that at the same time, you cannot measure energy and time together. There is always uncertainty, and this uncertainty, the minimum uncertainty for this measurement is h bar divided by 2, h bar half. So the minimum energy, it should be in this order. So it means there is something in vacuum. Energy of the vacuum can fluctuate. And by E equal mc square, energy is equivalent to matter. It means that in this situation, you cannot say that this is matter or energy. So they are converting to each other simultaneously at the same time. And so this just can be done in quantum world. And energy fluctuations can appear as additional particles called virtual particles. So it means that there are something in vacuum, and we call this as a virtual particle. It means that these particles, you think that it's not the real, but the effect of the existence of these particles creating something that we cannot neglect it. And this is about the quantum field theory. Okay, it's about fluctuation of the energy in a very small scale. And you can see here Casimir plates and vacuum fluctuation. This vacuum fluctuation, it's the source of Casimir force. Okay, so they discovered this effect and this force, and they use it in so they make it commercialized in micro electromechanical systems that is called MEMS, and also we have more smaller nano electromechanical systems that is called NEMS. And so micro, it's 10 to minus 6, nano is 10 to minus 9. And you can see here a MEMS. This is a micro-electromechanical system that it's pretty small in order of millimeter, and these small machines have a lot of application in drug delivery, in also in sensors. They can be used in automation and so on. So, for example, here you can see this is the insulin pump that was made in Switzerland, and we can see that this insulin pump is very, very small. in comparison even with this small finger. And so this is an example for MEMS. And so by using very small force like Casimir force, so the physics behind of this structure that is a small engine that you can use it in industry and in healthcare system that has been shown here. Okay. Another work that it was done by a physicist. It was actually he is a physicist called Professor Kordi, who measure he demonstrated a way to solve the formula for a plate and a cylinder, and you can just study this paper that is actually about the Casimir force in this reference. So in that time I was putting this reference in this PowerPoint. Okay. And in conclusion, the Casimir effect has become the subject of diverse studies of general physical interest in variety of fields. It is equally interesting and important for quantum field theory, condensed matter physics, gravitation, astrophysics, cosmology, atomic physics, and mathematical physics. Currently, the Casimir effect has been advanced as a new powerful test for hypothetical long-range interactions. At the end, I can say that it could be a good topic for studying. Okay, that was a review for this topic and a lesson of physics and also a little bit mathematics. Some of the references that I was using to prepare this talk, it has been shown here. And at the end, thank you very much for your attention. Bye.